Example 4 asks us, of all the closed curves in the plane, such as squares, triangles, and circles, with a perimeter of 10 meters, which one has the greatest area? So we're actually going to explore these three separately, and then try to find the maximum area for the square, the triangle, and the circle, and then with the constraint of a perimeter of 10 meters, and then we're going to figure out a conclusion that's going to give us the greatest area. So if we first consider the square, so for the square, we're going to have a objective function of a equals x squared. So that's our step 2, step 1, step 2, for first object being square, and a constraint of perimeter, so x 4 times 4x equals 10, and because there's only one variable here, there's only one possibility, so no differentiation is going to be required. So x is going to be equal to 5 halves, or 2.5, and I can plug that right into my area formula and get the area is 25 fourths square meters. Okay, so let's take a look at the next shape, which is a triangle. Now there are lots of ways to draw a triangle, and that's going to make a slight difference about which one has the largest area. So if you draw a triangle that has a, let me try again, one really short side, hopefully we'll notice that its area is not going to be as big as a triangle that has sides are the same length. So the triangle that's going to have the sides the same length is going to be the triangle that has the largest area, and so we're looking at the equilateral. So if we can argue that equilateral, we can argue that we are looking at an equilateral triangle, and so if these sides are called, say, CCC, and then I want to find its area, I'm going to have to find the hypotenuse, which I could find with the Pythagorean theorem, and calculate its area. So that new triangle, just to find that, I meant to say height. I was thinking of an H word and the wrong word came out. I need to find that height right there. So let's call that just for a second B. And then since this side is C, this side here is half of C, since we bisect, trying to find that height right there in the middle. And so I can find that B as my constraint function, but for the moment I know that the area of my triangle is going to be 1/2 of base times height. And so the base is C and the height is B, so it's 1/2 BC. So that's our objective function, and my constraint function here, solving for B in terms of C, is going to allow me to write this area function. So I know that B squared plus half of C squared is going to equal C squared. So that's B squared equals 3/4 of C squared. You got 1/4 here, subtract it off. And so B itself is going to be equal to the square root of 3/2C. So I can plug that into, this is part of step 3. And then the other part of step 3 is that since it's equilateral, all the edges, so 3C all the way around, has to equal 10. And so I actually know values for B and for C. So C is 10/3, and that means that B is 10 square root of 3/6. And so I know with those together that the area of this triangle is 1/2 times 10/3 times 10 square root of 3/6. So that is going to be, let's see, 25 square root of 3/9 if you multiply those together. Okay, so we're able to find the exact areas of these biggest possible shapes right here because I have so much information constraining them. And then we can talk about our circle as well. So it's getting us some practice relating the objective and the constraint functions, though not as much practice with the calculus pieces of it. Hopefully those are the pieces that we already have practice of already. And so our circles are defined by their radius. And so I know that my objective function would be area equals pi r squared, and the constraint is going to be the circumference needs to be 10, so 10 is going to be equal to 2 pi r, and so 5 divided by pi is equal to r. Plugging that in to our area function gives us an area for the circle of pi times 5 divided by pi squared, so that gives us 25 divided by pi. Okay, so out of these three shapes, we need to compare those areas. So I'm going to make them into decimals just to make it easier to compare. Let me clear off whatever I had there. So the first one for the square, we said it was 25 fourths, and so 25 fourths is 6.25 square meters. For the triangle, we said it was going to be 25 times the square root of 3 divided by 9, so that's worse. So that is 4.81 square meters. And for our circle, we said it was going to be 25 divided by pi square meters, so that's about 7.95 or 7.96 actually square meters. All right, so back over to the paper. Out of the three shapes that we've so far considered, squares, triangles, and our circles, so far at least the circles have had the largest area. Now there are other shapes that we haven't considered, such as parallelograms. I mean, out of squares and rectangles, squares should have the biggest area, so we got that covered. And anytime that you have any polygon, circles are going to perfect that polygon, so we can probably argue geometrically at least that circles are going to have the largest area. So circles have the largest area with a fixed perimeter. And so in this case, with a perimeter of 10 meters, the maximum area is 25 over pi square meters, which is approximately 7.96 square meters.